There we go. That's much better. Okay, thank you. Hello. Now, it looks like my power is not actually turning on, so we'll see how long I've actually got on this battery. Ni hao. Everyone's enjoying the conference, I hope? Yes? 非常好. I studied Chinese for a couple of years a long time ago, and I've forgotten most of it, but I'm trying to review here. So a little bit about me, first of all, to try and set the stage here. I work on JRuby, of course. This is the very rare red blue jay that can only be found in Photoshop. But it's kind of the new JRuby logo, and as you'll see on this slide, that is our new little guy there. He's JRuby, the Ruby J. And I'm from Minnesota. Has anybody been to Minnesota before? Oh, there's a couple of folks. Great, great. Yes, I am from Minnesota. I live in the beautiful city of Minneapolis. At least it's beautiful for about half of the year. Nice city, very warm climate in the summer, not so great in the winter. But it's a great city for a lot of my passions, like drinking beer. We have a whole bunch of different breweries now. There's a new one every couple days. I can't keep track of them. I also have played Go, Weiqi, on and off over the years. I'm not particularly good at it, but here I am white, and I soundly beat my opponent in this particular game. If anybody has a board nearby that they would like to play a game, I'd sure love to do that while I'm still here. Now, I mentioned that the weather is good for about half the year. We do have 4 real seasons in Minnesota. And we kind of like it that way, at least until February or March, when winter starts to get a little bit old. And by old, I mean suffering through temperatures like this. And you take a look at this entire week. And I think the next week was colder, actually. So we do have some pretty bitterly cold weather, which is naturally why I spend so much of my time in the rest of the world, where it's not below zero, way below zero all the time. These are all places that I've done talks on JRuby, Java, JVM stuff. I have not marked Taiwan yet because I'm still doing the talk. But it lets me go to places that are much warmer, much nicer, and meet wonderful people. This is a hedge maze at the resort in Goa, where RubyConf India was last month. Anybody that was at RubyConf India? Where are you guys? There's one part of the Ruby gang that we had there. But great event, a lot of fun. Goa was amazing, but it's probably not going to be there again. But if you have a chance to get to Goa sometime, it really was a nice area. And then, of course, being able to come to Taiwan is kind of a dream of mine, having studied Mandarin many years ago and had very few chances to exercise it. Here's the view from my hotel. Not too bad. I think if we go back here, I can see just top of Taipei 101 over the hill there. So that's good. I have seen it. I am going to try and go up it after the conference, but very exciting for me to be here, and I'm thrilled to be able to present everything to you all. Let's let it scroll again here. And scene. So I work on JRuby, and occasionally the Java, JVM stuff sneaks in there. My conferences are about evenly split between Ruby and JVM Java stuff. But in the process of working on JRuby, I've had to learn pretty much everything about executing code concurrently, optimizing JITs, how the garbage collectors work on the JVM. And as a result, I think we have a really nice implementation of Ruby in JRuby with real concurrent threads and so on. And I felt like it's time to start doing talks about how to do concurrency well in Ruby, what that means, and what you can get out of it. So let's get right into it. Now, the first question that I usually get from people is whether I'm talking about concurrency or whether I'm talking about parallelism. Two different concepts that it's important for us to separate right at the beginning. So concurrency means you've got 2 or more jobs, threads of execution essentially, 2 or more jobs that are running at the same time and making progress. It doesn't mean that necessarily at the exact same moment in time they're both executing. They may be doing a bit of work on one thread, a bit of work on the other thread, and going back and forth. But concurrency means making progress in two threads over a period of time. Parallelism, on the other hand, indicates that you are actually doing calculations, actually doing work at the exact same moment in time. Very different concepts that both play into this talk. So it's important to understand the two. So I'll give some examples of this to kind of illustrate. Thread APIs, as you've seen in Ruby and other languages, are a concurrency mechanism. They're an API for concurrency. They may or may not be actually parallel executing under the covers, as in implementations with a GIL or a GVL. The actor APIs that you've seen are also another concurrency model. Most API-level features are concurrency features. Parallelism is more a factor of how it is implemented, whether it actually runs those concurrent features truly in parallel. The native thread and process at that lower level, that's where you get into parallelism, if the underlying system supports it, if you actually have multiple cores to execute on. And then we have massively parallel systems now, SIMD operations, vector operations, GPUs, that are doing thousands of operations all at exactly the same time. So things are getting more and more parallel over time. And the reason for this is that while Moore's law has continued to be true, transistor counts have continued to double every, 1.5 years or so. The problem is that we've reached a limit on how much speed we can get out of a single core, a single execution. This is an example of the Haswell core, one of the newer Intel ones. I think it's the newest. I don't think they've announced the successor yet. But this is a 4-core Haswell system. The cores are actually the CPU cores are actually up at the top. Most of this stuff in the middle here is L1, L2 caching, some other units for doing memory I/O and so on, and then down here L3 cache that's shared across all the processes or all the processors. But the sneaky little thing here is that actually off to the side on the exact same core, this is a GPU core, an Intel GPU core built into the same processor. So not only are we getting the 4 general purpose cores on a typical Intel processor today, we are also getting a GPU that can do thousands of numerical operations at the same time. So it's very important that we start looking for better ways to run Ruby in parallel and write applications that can take advantage of it. So the bottom line here is that you really need both. You need concurrency. You need APIs that can represent doing jobs in the same general time, making progress on 2 jobs or more. But you also need parallelism to actually take advantage of the hardware. Concurrency without parallelism is not nearly as useful as having both together. So let's talk a little bit about the different types of process-level concurrency or how you can achieve these. So with you can use threads. A lot of folks end up just doing process-level concurrency, as in MRI, when you fork a process or you spin up multiple servers. That actually does get you multiple cores utilized. You actually are able to take advantage of all the hardware in the system, but you have communication overheads. You have memory requirements for all these separate processes. It's certainly simpler. It's a lower risk way to do concurrency than to do threading, but it does have its downsides. And so we're not going to be talking too much about process-level concurrency in this talk. Now, thread-level concurrency, which is what I'm going to be covering for the most part, is all in process, shared memory, but the threads actually can run on separate cores and can actually take advantage of all those cores at the same time. It's definitely higher risk. Anytime that you have multiple threads of execution that have to share memory, maybe be updating collections, maybe be modifying data somewhere, there's a risk that you're going to step on updates. There's a risk that you're going to just blow up and have an error at some point. So there is more risk involved in this, but the benefits are huge. If you want to run 20 concurrent users on a web application, you can just throw 20 threads at it, and you're done. You don't have to spin up 20 instances of a process. It makes a big difference as far as the cost of running a large-scale application. We also don't have any communication overhead. Being able to just write to memory and read from memory is about as fast as you're going to get for communication between two threads or processes, and it's far less overhead than doing out-of-process communication for process-level or process-like concurrency. This chart here is you can come back to this at some point, but this is basically a few of the more popular runtimes that you folks might have used, that might be familiar with. Of these, JRuby and, well, essentially a JVM, JRuby on the JVM, and Rubinius are the only ones that actually have concurrency and parallelism. All the MRI releases have concurrency. There is a threading API, but the threads are not allowed to run concurrently. There was a question earlier whether Topaz supports concurrency or parallelism. It supports neither because it doesn't have the thread API even implemented yet. Also, the PyPy framework can't really support parallelism just yet. They're still trying to figure out a better way to do that. But this is kind of the state of affairs. And I want to try and go through some examples of why it's important that we start looking more for concurrency and having more parallel execution of code. So this is my system when I'm not doing anything. Pretty quiet, little bits and pieces of stuff going on. But this is kind of a baseline for us to do some comparisons between Ruby implementations. I'm using a little thread scaling benchmark that some of the folks at Sun wrote for us when we were there. Basically just creates a bunch of big strings and then manually goes through and reverses all of them. It's busy work. Just trying to test whether thread scaling is actually close to linear as far as the amount of work going on. So this is our example. Now if I run this on Ruby 1.8.7, what you'll end up seeing is that no thread ends up running at the same time. Ruby 1.8.7 has what's called green threads. The threads that you create all get scheduled into the same native thread, the same CPU kernel level thread, and they have to share that one thread. So there's not even any opportunity for them to run on multiple cores. You look at 8 threads, same thing. So we're not talking about any parallelism at all here. The time slices go to each thread. They never can actually run in parallel. I'm talking about how this actually works. Time slicing in Ruby 1.8, very rough diagram of this. Every so often, I believe it was 10 milliseconds or so, that it sent a ping, used a signal to ping the process and say, okay, stop this current thread, let somebody else run for a while. And so every 10 milliseconds, if you were done with your work or not, you had to turn over the thread, turn over execution to another Ruby thread in the same process. And if you wanted to block and do an I/O blocking call, or you wanted to explicitly give up control, you could also do that too. But everything in Ruby kind of ran with these little 10 millisecond slices. And so that's why we end up not actually having anything run on multiple cores at the same time. Now, Ruby 1.9 did actually move so that each Ruby thread was mapped to a real native thread. But unfortunately, none of these threads are allowed to execute in parallel for various reasons. Internals of Ruby aren't quite thread safe in MRI, things like that. It's a little bit different model here. We have a global VM lock. So all these threads are essentially running at the same time, but most of them are sitting and waiting to acquire this lock. Only one person can have that global VM lock at a time, which results in only one thread actually using the CPU cores. The other ones are sitting idle, waiting to have a chance to run. And so essentially it's the same effect. We don't have actual parallel threads, even though they actually do look like native threads on the kernel level. Here's a little tweet that was sent out for the RubyConf India, and a great reply by Andrew Grimm. I also noticed that we had some concurrency issues with lunch yesterday. Everyone was lined up out the door. Everything was in serial. Now, if we look at the 8 threads model in 1.9, it does sort of look like there's some parallelism going on. At least the bits and pieces of the CPU graph here are finer grained. But actually, if you zoom in on this, it's very difficult to find anywhere that 2 CPUs are being actually used at the same time. In fact, there's a few places where it's very obvious. Here, this is one CPU, and the others are not really doing anything at all. Again, here. And so you can see that even though the slicing is a little bit finer, it's able to get more threads into the cores, they're not actually using them at the same time. And now here's JRuby running the same benchmark with one thread. This is actually JRuby with 3 different JVM garbage collectors. You can configure them at the command line. Now what you'll notice here is that even with one thread, we actually are seeing some parallelism. This core is probably at 30, 40%. This core is probably at 20%, 20, 20. So we're well over one core's worth of work being done. Now why is this? I actually had to kind of look into this myself just to make sure I understood. So why do we see some parallelism even with one core in JRuby? Well, the JVM has a number of GCs. I think it's 4 or 5 now, and that's just Hotspot, the OpenJDK JVM. There's GCs that have concurrent options and parallel options. They'll run while your application is still going concurrently, so your application doesn't have to stop. The parallel collector will just spin up a bunch of threads when it has to do GC to make sure it gets as much work done as it can. There are also threads for the JVM's JIT behind the scenes. As it's turning Java bytecode into native code, it does that in the background. Signal handling, monitoring threads. You'll notice that when you start up a JRuby process, there's probably 15 to 20 threads, even though you've just got the main thread that you're using, because the VM does a lot of threading on its own. And so in this case, the serial GC at the beginning here, this is the one where we don't see as much parallelism. It actually is just running as a single thread. It doesn't spin up anymore. The other two, the parallel GC and the concurrent GC, we actually do end up using multiple cores. So it's important to remember this. Not only is JRuby able to have real parallel user threads, there's parallel GC, concurrent GC that's also happening for you. So you won't have GC pauses as much. Now the fun part is when we actually go to JRuby with 8 threads. Completely different story from MRI, of course, because these threads are actually running concurrently. And now we're probably not getting actually 8 threads out of this. They're GC threads, again, that are continuing to do work. But with JRuby, we actually can completely saturate the system with a single process. And that's extremely important for making an efficient application these days. Now, interesting to note, we're also quite a bit faster than MRI, quite a bit faster than pretty much all the Ruby implementations. And some of this is due to the concurrency, but a lot of this is also the JVM does an incredible job of optimizing code. So we want to be able to do concurrency. We want to be able to do it safely. These are kind of the 4 rules that functional programmers over the years have come up with, multi-threaded programmers have come up with. I've kind of refined them down to these 4 that I think kind of spells out how to do threading safely. We're going to go through each of these one at a time. So the first rule of concurrency is don't do it if you don't have to. There are lots of pitfalls along the way. There are lots of algorithms that may not parallelize very well. Lots of different cases where threading is not going to automatically gain you performance and may actually cost you performance in some cases. So there's this first step that you need to do to evaluate whether threading, whether parallelism is actually valid for your application. An example that I worked on for this talk, I wrote a little Ruby script. It's a sequence counter. It just goes through a file, looks for sequences of letters, and then counts up what are the most common sequences in that file. So it needs to read it all in, and then process every single line of that looking for character sequences. Here is part of the code from the single-threaded version. Open up a file here. I'm just using a large dictionary file. We've got hashes where we're going to keep the count of all the different sequences. And then down here we do some unpacking. We iterate over all of them and then stuff them back into the sequences, incrementing the number each time. So this will be our example for going forward. Like I mentioned, I'm processing a dictionary file. It's just the user shared dict file. I ended up creating a really big one to try and do some more parallel testing, but it looks kind of like this. And if you want to go check this out at the repository, it's just sequence counter on my GitHub, headius/sequence counter. You'll notice that there's multiple numeric versions here. What I did when I started working on this is write a very naive version at first, and then continue to improve it over time. My naive version, when I ran it with a single thread, it looked something like this at the beginning. It was actually using up almost all of the cores just for that one thread, and I had to investigate why. So I wrote my naive algorithm. I measured it for a certain number of time. And then I continued to iterate on it and improve it. Try to find things that would reduce the overhead. Make the single-threaded version run as fast as I possibly could make it. Very important step before you start going to threading. If your application is wasteful and slow, it's very likely that threading is not going to gain you a whole lot. You need to have an application that is at least doing the best it can in a single thread before you can even consider going to concurrency. So I did my little fixes and managed to improve the single-threaded version quite a bit. Streaming from the file rather than reading it all into memory was probably the biggest one. I couldn't do anything while I was waiting for the file data to come in before. What it turned out was that before the concurrency work, I had way too much allocation, many objects being created and thrown away. So I worked to reduce that, so there's less GC as well. The GC is not working as hard. It was actually the garbage collector that was using up all those cores before. Fix some algorithmic complexity issues. I had a few of those. If you have like an n-cubed complexity algorithm, chances are throwing threads at it is probably not going to help you a whole lot. You're going to need to re-examine how you're actually doing that work. And then, very important that if you want to do concurrency, make sure you're testing on the runtime that you intend to use. I always hear from people that claim their Ruby library is thread safe, and then I go to Travis and see that they only test on MRI. Not very good way to make sure that your concurrency is actually up to scratch and you're thread safe in your application if you're not actually running in parallel. So at this point, if you've done all these things and you've got a good solid single-threaded algorithm, single-threaded application, and it still seems like performance is not very good, chances are that threading may not be the answer for it. There's also going to be cases where it's just too hard to split up the work across multiple threads. So the bottom line, the main reason why you would not want to do concurrency, other than the fact that it's kind of tricky sometimes, is that it really can't help code that's already using all the available hardware resources. My single-threaded version of that script was using up all the cores because it was creating too much garbage. The GC was working too hard. Threads won't help me there. There's nothing left for the computer to do. So rule number 2 about concurrency, if you have to do it, then at least don't share data between your different threads, between your concurrent executions. So that makes process-level concurrency fit very well. They don't share a whole lot of data. Anything that they do share, they're usually message passing, doing an out-of-process call of some kind to a cache or something. They do have to sync up eventually if you're going to be doing work with a final result as part of the process-level concurrency. But usually that's a last phase. I'm not going to talk a whole lot about rule number 2 because it's not really the most useful concurrency. If you have two parallel threads that never see the same data, they're not really working together. So it's not a model that I would consider a good way to do concurrency. So 3, and this may be a sweet spot for going forward, and it certainly is for functional languages and functional style programming, is to just make sure that if you are sharing data, you're only sharing immutable data. Any thread that has data in hand then, has a reference to an object, knows that it's not going to change. Don't have to do locking, don't have to have a lot of complicated safeguards to make sure that the threads don't step on each other. Now there's a few ways we can do this in Ruby. Probably the simplest is object freeze, or was it adamantium, I think was the gem that was mentioned, that can do deep freezing of objects as well. Just make sure that whenever you hand an object off and make it visible to other threads, that you've frozen it or made it immutable in some other way. There are a few patterns here. Obviously, if it's read-only, you just make all of your changes, freeze it, and then stick it out in public, and you're done. If you need to make occasional updates after that, a good pattern for standard objects and collections that aren't specialized for threading, make a copy of it, make your change, and then put your copy back in that variable or constant. It's a good way for doing caching that doesn't need to be written a whole lot. Usually it should be hits from the cache. If you have an application that is doing mostly writes, though, this is not going to be a great way to scale. Every time you do a write, you're going to end up doing a copy, an O of n operation, making your modification and putting it back. So you're going to lose a lot of cycles that way. So there are some immutable data structures out there that make this a little bit easier, designed for being immutable and efficient at the same time. Probably the most interesting are the persistent data structures that have been coming out lately, been used in languages like Clojure, now available for Ruby as well. You can look up C-tree, which is a concurrent hash array mapped tree, or just a hash array mapped tree, which is the structure that's in Clojure. Now, what does persistent mean here? Arne mentioned it here, and he had a pretty good description too. The general idea with a persistent collection is that if you have a reference to this collection, it's always going to look the same. Nothing is ever going to change that behind the scenes. If you need to make a change to it, you get a new reference to a new collection. And it's done internally with various tree traversal algorithms, various structures internally to make sure that it's efficient and only has to modify a small amount of that collection. But every time you're going to get a new reference out, and it's safe. It's 100% safe all the time. You can understand why this is popular for concurrency. You know that there's no chance that this collection is ever going to change while you're working with it. The library that is currently available for doing persistent collections, persistent data structures on Ruby is called Hamster. You can gem install Hamster, and you get a bunch of collection implementations that are based on this hash array map tree, based on the same thing that Clojure uses. And essentially, this was a port of the Clojure collections into pure Ruby. Works on all implementations. An example of using this. So here we're creating a hash. We get our hash at the top. Looks fairly simple, almost like making a Ruby hash with a hash.new. Then you'll notice down here we can get the values out of it. But when we finally need to make a change, we need to put another person in here, we have a new reference coming out of it. So from our person collection, our person hash that we had at the beginning, when we make a modification, we've got a new reference. It's kind of like a diff. Like every time you make a modification to this collection, it diffs it, and you get a new version of it. Also coming soon, there is some performance issues with Hamster currently. I've tried to improve some of them, tried to help the folks that developed it make it run faster. However, it still is not where we want it to be able to replace array or replace hash in a really high concurrency application. So there's a re-implementation of this going on. Smit Shah, who did the new bundler resolver, is working on a native implementation of persistent data structures. First for JRuby, and then we'll also have one that works with CRuby as well, where all of the heavy lifting is done in native code, essentially. It's considerably faster. So this is one to watch for if you want to use persistent structures in the future. Other techniques here. You can use known immutable data, as was referred to in Arne's talk, values that cannot be mutated. You always know that a symbol is going to be exactly the same when you pass it around threads. Same thing with numerics and other core types in Ruby. You can do your mutation, do your modifying of a collection for a little while, and then do the freeze, as I mentioned earlier. You can just do this handoff. If you are working with a mutable data structure, once you give it away, once you pass it to another thread, assume you can't touch it anymore. That works fine too. You don't even need to use freezing or immutable data structures if you're good about always giving up control over it. And I think that's probably about it as far as trying to avoid mutable data. There is a lot of applications where you're just going to have to use mutable data in place. Even in the case of Clojure, there are now collections or models or certain ways to write code that within a given context, it's just a plain mutable collection. Performance-wise, there are things that you can't do with a hash array map tree. So the fourth rule of concurrency is that if you must do concurrency and you need to share data, you're going to have to find some way to at least synchronize all of that modification of that data. Synchronize the updates of your hash or array. And this is where things start to get a little bit tricky. So first of all, I'll talk about some of the data structures that we're dealing with. Most of the core structures in Ruby are not guaranteed to be thread safe. On MRI, they may appear to be thread safe for certain cases because they don't actually run in parallel. But on JRuby, array, string, hash, and so on, if you try to do concurrent updates, concurrent writes and reads into those, you will eventually get something to blow up. There are various reasons for this. Here is a chart showing a few of them as well. In order to get the fastest possible array or the fastest possible hash, it's just not affordable for us to do locking around every single operation. And as any Rubyist knows, hashes and arrays and strings are everywhere all the time. We need those to be small and fast and not have a lot of locking and threading overhead. So we made the decision early on that those collections would not be thread safe in JRuby. You'd need to use some other mechanism or a different type of collection. Now Q, however, which is part of core, is actually thread safe. So let's talk a little bit about how you can use queues as a first step for concurrency. So we have Q and sized Q. Q is basically unbounded. It'll just get larger and larger as items are put into it up to the limits of your memory, whereas sized Q will have an upper bound. It'll only allow a certain number of items to be in the queue, and then subsequent pushes will block until it can open up. Perfect way for you to pipeline data, send data back and forth between threads. Push some data on a queue with one thread, pop it off the queue with another thread, guaranteed to be safe, and ideally it should be really fast. It's mostly just a handoff between the two threads at that point. And as I say, this is standard in all Ruby implementations. So go back to this is part of some more code from my sequence counter example. In the main thread here, we want to start splitting this work up. So for this particular version of it, I decided that about every 50 lines was a good chunk of work to do in each thread. So for each 50 lines that come out of that file, I stick them into a queue. Now, on the thread side, each of those threads is just going to continue to loop over time, pulling those chunks of data off of the queue, processing it, and then storing it somewhere, which I'm not showing in this slide. But it's fairly simple. It's a nice, clean way for you to pass work out to threads. And actually, what I don't have, I removed some code here. I wanted to have all of these threads print out some updates as they went. Well, if you've ever done printing, puts in a thread or in multiple threads, you'll know that you get data that's kind of spliced together and formats really weird. In order to avoid that, I used another queue. I pushed those messages onto that queue, and I had a thread that would just go and look at that queue, print it to standard out. Very easy to start passing data around and get some concurrency quickly. Now there are some other collections, specialized collections that are out there in gems available for you to use. The thread-safe gem provides fully synchronized, fully locked arrays and hashes. All reads and all writes are synchronized so that there's never going to be two threads making modifications at the same time. That works okay. It's a naive approach to doing thread-safe data structures, but it does work. If you end up having a lot of threads always trying to work with these, you're going to see some bottlenecks. So it's not the best way to make those data structures safe, but if it's not too many threads hitting them at the same time, it should be okay. It also provides a much more useful structure called cache, which is basically a hash implementation that is guaranteed to be thread safe, but it does it in a very efficient way without it using any locking internally. The reason that it's a separate class in here is because of the way it's designed, because of the way that data structure is implemented, it can't support all of hash's features, so we figured we'd call it something else. On JRuby, of course, you have all of the Java util concurrent classes. You can go out and find some excellent books, excellent documentation on them. Java Concurrency, I believe, is a book by Brian Getz that's a good one to look at. But tons of tools, including collections, for doing concurrency and all thread-safe stuff. Now, if you don't have these collections or you've got your own data structures that you've implemented, locks may have to come into this. You may end up having to use some locking. So when you use locking, you're basically synchronizing around all accesses. For sure, synchronizing concurrent writes so that threads don't step on each other, but potentially also having to synchronize the reads. If it turns out that a write can cause a read to fail or blow up, as with arrays in JRuby, you need to lock around both writes and reads. It's usually just safe to do both if you're going to be locking at all. Now, if you get to too many locks, or you're hitting these locks too hard, that's going to damage concurrency. It's something that you have to weigh into it. Locking can be very expensive. You want to try and hold the lock for the shortest amount of time possible. Don't do large blocks of work all inside of a lock, because you're guaranteeing that no one else is ever going to get any work done during that period of code. The other aspect here is that if you have multiple locks, it can lead to deadlocking. And a deadlock is essentially two threads both waiting for each other to give up a different lock. And they're sitting there, stuck on that. Thread A has a lock that thread B wants, and thread B has a lock that A wants. The simple way to avoid this is just to make sure that your locking and unlocking is always done in the same order everywhere you do it. It's impossible to have deadlocking if you follow that rule. It's not an easy rule to follow at times if you've got locks all over the place, but that's the simplest rule to avoid deadlocking. And in Ruby, the simplest lock that we have is mutex. It's a standard class. You don't have to require it anymore. It used to be a library in Ruby 1.8. But it's just available, top-level namespace, always there. Some examples of using mutex. Actually, this is an example of monitor, but it's basically the same thing. So we create a new one, create a new instance of a monitor or mutex. We lock it. We do some work, and then we unlock it. That's probably the simplest way to get some thread-safe code in the middle. You can also sleep, and that while you own the lock, while you've got this lock in hand, you can give it up for a short period of time. Perhaps you're waiting for some data to come off the wire. Perhaps you're waiting for some user input before you continue on with some work. You can pause your lock for a while. You can also try to acquire the lock, and if somebody else already has it, it won't sit there and wait for it. It'll tell you, I can't give you the lock right now. You can go on and do some other work. Finally, at the bottom, a slightly simpler form, rather than having to always remember to do lock and unlock. And unlock here, you always should make sure that you're doing it in an ensure block so that you're unlocking it for no matter what happens, errors and otherwise. But lock.synchronize down here basically does that for you. Pass it a block of code. It will safely lock the mutex, run your code, and then unlock it on the way out. Now, I mentioned that locks are a bit of a concurrency problem at times. Can we avoid them? What can we do? Well, there are another class of operations that we can do, atomic operations, where we're safely swapping data in and out of memory without having locking involved, without the threads stepping on each other. Easier to show this in an example. So here's an example that uses Hamster and the atomic gem, which is, I believe, the only library for doing atomic operations on Ruby right now. And it works on Ruby, JRuby, Rubinius, any of them. In our example here, we create a new hash, similar to before. Then we create a new atomic reference here, giving it the people object to start. So we've got our atomic reference. It's got our initial collection in it. Down here, when we want to make an update, atomic.get gives us our hats collection back. It's a persistent hash from Hamster. We make our modification, add another name to our table, and we get our new reference out. Now, at this point, we certainly could just go right back in and force it into the atomic reference. That wouldn't be very useful because we're not actually using the atomic features of this library. You could just be using a variable at this point. You're very likely going to step on somebody else that's making the same updates. Two threads will come in, modify the collection, and one of them will lose. Better is down at the bottom, an example. Whoops, whoa, wrong button. Okay, down at the bottom here, why don't we replace it only if somebody else hasn't already made a change? And that's what compare and swap does. This, on JRuby at least, I believe also with the MRI implementation of atomic, this basically boils down to a single assembly instruction. It checks first if we actually still have the old hats collection in there before making the update. If somebody else has come in behind us and changed it while we were doing our work, this will return false, and we'll know that we need to do it all over again. Reacquire that collection, make our change, and try to do the safe update again. Now, the advantage of this is that we're not using any locking at all, and This boiling down to just a single assembly instruction, this is going to be much safer than, for example, having a thread unsafe collection, an unsafe collection like basic hash or array, and using a mutex to make it safe. All right, so putting all this stuff together, I already covered a lot of tools and a lot of techniques for doing concurrency. There's a lot of stuff to remember about this. Most of you, I'm hoping, will not have to build your own concurrency system, your own parallelism into your application, because there are some folks out there who've done excellent libraries that do a lot of this work for you. So let's move on and take a look at those. Is anybody using Celluloid? Okay, great. There are a few folks. Celluloid is an implementation of the actor model. Actors are basically just concurrent little entities that you send messages to, sometimes get messages back. They run on their own. All you ever do is pass them data as messages. So it's an implementation of the actor model, but it's kind of done with more of an object-oriented Ruby sensibility. All of the actors in Celluloid look like normal classes. You make calls to them that look like normal calls. However, behind the scenes, it turns those into actor messages, it runs those on multiple threads, and handles all the synchronization, all of the locking and other stuff for you behind the scenes. There's also a great ecosystem that's coming up around this. Celluloid I/O, if you're going to be doing blocking I/O in your Celluloid actors, you can use Celluloid I/O to make sure that the actor that thread isn't stuck while it's doing that work. Real is a web server, application server, based on Celluloid that uses actors for each of the requests that come in. And dcell, I think, is still early days, but it's kind of exciting. Distributed actors. So even the same nice code that you have with Celluloid on a local actor can work with an actor that's in a different machine in a different city. Quick example of Celluloid here. This is actually from the Celluloid wiki. So we have our Sheen class. We're going to be tracking all of the Sheen actors in our application. We can set it up with a name. We can set what their status is, whether they're working on a movie or doing something else. And then we can report what they're doing. We can check on the data. Now, to make this simple class into a Celluloid actor, we only have to do this. It's a done deal. So then, with just two modifications, 2 lines of code added to this file, we now have a parallelism capable, a concurrency capable version of our Sheen object. Oh, and there goes my battery starting to complain. Okay, we'll keep going. I think I'm almost done here. So we'll create our Charlie Sheen object up at the top. And what you'll notice here is rather than getting just a plain old Sheen object, new actually gives us a Celluloid actor that wraps that object. That's the actor that we're actually going to be sending messages to. Or it's a proxy, a representation of an actor running on a thread somewhere in memory. So we've got our actor. We'll set the status. Charlie Sheen is winning. We can see that it's been updated. So this is just a plain synchronous call, and it will wait until that thread has gotten the message, processed it, and finished giving us a result back. We can also do that asynchronously just by adding the async call here, which gives us an asynchronous proxy to the actor. Then when we do our set status call, it returns nil immediately. The message is put into a queue somewhere, and the actor can go and pick it up and do whatever work it needs to do. Sort of like our queuing example earlier, but we don't have to manage the queues. We don't have to deal with shutting them down and making sure that they're still operating properly. And then down at the bottom, we let some time pass, check the report, and it did eventually, the thread did pick it up, and it did actually do the work. Now, moving a level up from Celluloid, we have Sidekick. Sidekick is a very nice background job API, really scales well, and it's based on Celluloid, actually. So think something like rescue or delayed job or whatever, but this is definitely far better than the other options that are available for you. So again, a normal looking Ruby class, that's your job. You tell Sidekick to go off and make that into a background job and run it somewhere. It uses Celluloid and its actors to schedule that work, threading all taken care of for you. Don't have to worry about any of the synchronization issues. Now the last aggregate library, the last specialized library I want to talk about is the Concurrent Ruby library. This is a fairly new development. I think it was just announced at RubyConf this past fall. And at this point, there's something like a dozen people that are committing to it on a pretty regular basis, moving very quickly, and this is a very exciting library. It's exciting because it has damn near every threading concurrency utility you can imagine. A bunch of stuff that isn't even available on the JDK, on the JVM, which has tons of concurrency tools. Actors, agents, promises, such as from JavaScript, scheduled tasks, executors, thread pools, timeout mechanisms, all sorts of stuff, way more than I could list on this slide. It's like he's taken every concurrency thing from every language that's out there and made a Ruby implementation of it. And now they're actually going in and they're adding some native bits to speed it up on particular implementations. Very exciting library to check out in the future. Periodic releases, so it's moving along very well now. And examples, everything that I've shown you and way more. There's collections, there's queues, there's all that stuff. So a great library for starting to build a nice concurrent system. So now the payoff from this, obviously, if we're going to do the threading, we want to see what the results are. This is the sequence counter we had before. The unthreaded version running the 23 million line file took about 65 seconds or 60 seconds or so. And then 2 threads was about half as long. 4 threads was about half that again. Did all that front-end work to make sure the algorithm was efficient, used a queue, used some simple threading to break up the work, and actually pretty much doubling the amount of work we're getting done in the same amount of time. And this is the real payoff. This is why it's important for Ruby's future to be concurrent, so that we can do things like this. So recap. Ruby's future really must include concurrency. I think there's been half a dozen talks here that were heavy on concurrency, talking about STMs, talking about some functional programming ideas, talking about just plain old concurrency in Ruby. This is obviously one of the most important areas where Ruby needs to grow. And the tools are out there more and more. 2 years ago, 3 years ago, none of the stuff that I showed you existed. This is a very exciting time for concurrency on Ruby. And there's more that can be done. The Concurrent Ruby project needs people to help out. Celluloid needs people to help out. We need to work together. I want to help you understand how to do threading well, how to build these libraries, how to use these libraries. And I need you to show us what you're doing and try and help us find new concurrency models, find better implementations, find better ways to utilize the system so that we can take Ruby forward to the future and make sure that it actually is concurrent and parallel at the same time. And that's all I've got. Thank you.
If you have any question, please raise your hand. Thank you.
STM in Ruby? There was a talk earlier today about STM. Hopefully some of you were able to see that. STM is software transactional memory. Essentially, you can do multiple updates to a data structure, to some object, and then sort of commit them as a single transaction. It'll either fail all at once or it'll succeed all at once. Closure uses this internally for doing safe updates of references to collections, for example. Yes, I believe it's certainly possible. I have a gem out there called Cloby that was an experiment of mine to use Closure's STM in JRuby. It only works on JRuby. But what it gives you is a Closure object that you can extend and a top-level do sync method that is your synchronized transaction. All of the updates for your instance variables then become transactional, and they will fail or succeed as a single unit. So already it is sort of available. I'd like there to be one that works across Ruby implementations, a standard STM API for Ruby. Hopefully that's the sort of thing that we can start working on together. So it's definitely possible, and there's early implementations already. Other questions? I must have done a good job. All right. Well, thank you very much.